Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our speaker today is Milena Mihail, and let me tell one short story she might remember about. So one thing common between me and my advisor was our wife's birthdays. So there was this thing, I won't tell the birthdays. It was my wife's birthday. I was newly married, so I was taking off. And so supposedly Vijay told Milena at home, Kamal didn't come to office today. He was, because it was his wife's birthday. And then Milena told me next day, he didn't remember it was my birthday too. Anyway, here is Milena.
Thank you. So I'll be talking about, so the title is the conductance of random inner product graphs, and this is joint work with my former student, Stephen Young, who is now a postdoc at UCSD. And so these are really, random graph models, strict Erdős-Renyi generalizations. And the more general context in, exploring their conductance is that we are obtaining these generalizations trying to get to mathematical models, but whose properties are closer to the properties of real graphs as we observe them in complex networks. And so now something fun is going to happen, and I don't know why, but there is some animation. I didn't put it there, but anyway. So I hope it's the only place that it happens. I don't know how it happened. So this is the outline of the talk. Well, usually one starts with context, but I don't want to start by giving pictures, So I will just start with two theorems, and I will go through the conductance primitives, very, very fast, because I think everybody in this room knows them. And then I will say in which context sort of we're trying to get these more general theorems. And it's the context of what kind of random graphs are modeling real complex networks. And in particular, then I will go on to say how existing random graphs have discrepancies from real networks. And then I will introduce the random inner product graph model as one candidate to extend the parameters of random graphs and allow them to come closer to real networks. And then I will talk, what tools, technical tools do we use to analyze their conductance and, give a flavor of the theorems and further directions. Okay. So, all right. So, well, the conductance is of a set is how many edges cross from the set to its complement divided by the sum of the degrees inside the set. And it's a very well-known quantity, and in different contexts you want to show different things about it. Many times we want to show that the conductance is very large so that algorithms work very fast. In social networks, you're actually interested in particular sets that have small conductance because they're indicative of communities and they exist, and perhaps you want to model them. So, so just one thing to remember is that, just what is the conductance of a set in the context of real networks. We need to see, what is the size of the sets that exhibit worst conductance, how many they are. These are questions that sort of, some of them are folklore and some of them we've touched, so we sort of know anecdotically. But, as we're getting more into the detail of the networks, these will be questions that will be coming up. And of course, the conductance of the entire graph is the conductance of the worst. Is the conductance of the sort of worst set. And there's a classic theorem that, I mean, of course, this is a hard quantity to compute, but it can be bounded in a pretty tight way from above and from below by the second eigenvalue of a certain matrix. I will come to this, to the matrix later, but the point is that there is, there's a second eigenvalue of a certain matrix that bounds the conductance of a graph from above and from below. And so here is one theorem. So now here I come to my two theorems. So here's one theorem. It is due to Chung, Liu, and Wu, and it is one generalization of Erdos-Renyi graphs. So they call this the expected degree sequence model, and it goes like this. So you have targeted degrees W1 up to Wn. So the smallest degree has to be large enough. I mean, one would have hoped for C log n, but okay, it's C is some constant log squared n. So you want the smallest degree to be large enough at least to get connectivity. And the largest degree is has to be less than the square root of the sum of the degrees, the volume of the graph. So if, for example, you have you had n log squared n volume, the largest degree would have been bounded by some square root of n times log n. It's a it's a strong condition. It is not necessarily the case that I mean, why wouldn't you allow? Why wouldn't you have a model where you would allow the largest degree to be larger? So, but anyway, so we're given a sequence which is a target of degrees, and this is how we form a random graph that the probability of an edge between I and j is proportional to the expected degree of I, expected degree of j, divided by the sum of the degrees. So the justification of this constraint was that so that this is a probability, but it's really a little bit more serious. It comes in a crucial way in the proof, and this is a little bit troublesome. So okay, so but in this model, which is a generalization of Erdos-Renyi, you get lambda too small, and you get constant conductance with high probability. All the statements are with high probability. And here's another way to think about this theorem. So why should I have target degrees, right? So instead, I can just say that there are points, and n points, and they have weights, right? So the lowest point has, very small significance, and the highest point, okay, so this should be less than or equal to 1, has, could have significance as much as 1, right? And then you connect to points with probabilities proportional to their significance. It's equivalent to the previous model. I'm just stating it in terms of real numbers. And then again, you can get a bound that the second eigenvalue is bounded away from 1. The conductance is large. Okay. Now, what is missing from this picture if we think of them as weights? Well, why should the highest weight be 1? Well, perhaps the highest weight should be, you can go all the way to, it could be n or something, and then here you could take the minimum of 1 and the products, or you could just bound it by something that makes sense, sort of maybe n over log squared n, but and allow for the whole range of graphs that you can get. And I mean, intuitively, allowing more connectivity on the higher degree nodes should not harm your conductance. Should only improve the situation, but no. So the known techniques have this constraint. So this is another way of thinking of the Chung, Lu, and Wu theorem. And now, if we start thinking about these real numbers as weights, well, then maybe they're not necessarily on a line. So let's think of them as lying, okay, maybe in 2 dimensions. In a two-dimensional in two-dimensional space, and each point has a weight, but the probability that they are connected is proportional to the product of the products of their weights and the cosine of the angle that the corresponding vectors form, right? So that says that if we are in the same direction, then yes, it is the product of our relative weights. But maybe we have something. We have some differences also. So we will connect with lower probability. And one would expect that if the angle of this cone is small enough, so that so that the cosine is large enough, one would get a similar theorem. And the answer is yes, of course. For an angle that is small enough so that the cosine is at least, I don't know, a little bit more than 1/2, So if the angle is small enough, then again you get constant conductance, and of course you pay a little bit of penalty because you had these. Because the probability, the connectivity probabilities where there was a cosine of angles of vectors involved. Okay, and now I want to say a little bit about the proof techniques of how one gets, yes? Pardon me?
About the statement, should you expect this inverse golden ratio to be sharp, this sigma 0?
Do I expect it to be sharp? No.
So anything positive should be okay? Any positive lower bound?
Yes. So whenever the angle, and this is essentially the final theorem that I will show. Okay. So as long as you do not have complete orthogonality, right? So as long as you are within a cone bounded away, I mean, of course, you'll get conductance. But the frustrating thing, and this is what I'm trying to project, I'm not sure I'm doing a good job, is that, here is, an elementary case, an elementary sort of extension of Erdős-Rényi, right? And, we have a lower bound. Okay, so let me put it here. Yeah. So first of all, look at the lower bound. Why should it be log squared n? I mean, log n is good enough. I mean, why should it be that there is no reason that having larger and larger degrees you should pay a penalty on the conductance or on the second eigenvalue. Because the denser parts of the graph, the larger cliques are in the denser parts of the graph, and it's just indicative of perhaps the limitations of our techniques rather than anything else. And plus, there's the very frustrating upper bound. I mean, why does the maximum degree have to be square root of the volume?
But you need that upper bound for your result.
It is implicit, yes. Oh, yeah. Oh, well, yeah, sure. Yeah, it's at most 1, I'm saying, right? And I think that the result should hold for, anything. And just take the minimum of 1 and xi times xj. And this limitation is not only in this sort of expected degree sequence or inner product model or whatever. It's also in the configurational model. So, I mean, we seem to be bounded by the largest degree being the square root of the volume of the graph. And, I think it's a indication of the limitations of the techniques that.
But can you do some simple truncation and throw away the large or reduce number? The conductance is monotone.
No.
I would be very interested.
Because
I would be very. It's not monotone if you increase the number of edges.
It's not.
because the denominator has a volume.
Yes,
Okay, yes.
but I would be very interested to talk about it in particular with you. too. I think these are just they speak about the limitations of our techniques rather than the graphs themselves. And okay, so let's keep going. Okay, so let me just say what proof techniques are known for this. So the quantity that is relevant to conductance is the second eigenvalue of the adjacency matrix of the generated random graph. D to the -1. D is the diagonal of the degrees. This is pretty standard, okay? And then in order to get a bound on this quantity, it's the same as, because we know what is, well, first of all, we orthonormalize, so the relative quantity now becomes, whatever this expression is. But it has to do with the diagonal of the degrees in the adjacency matrix. And then we know what the first eigenvector is, so we project to a space vertical to the space of the first eigenvector, so we just remove it, and now we're looking at the first eigenvalue in the projected space, which is the second eigenvalue in the original space. All right, so the difficulty with dealing with these quantities is that there are random variables everywhere. Okay, so the degrees are random variables, but the adjacency matrix, the entries are random variables. So, so everybody when we're dealing with these things, the first thing is we try to control variability in different ways. So let me tell you sort of the ultimate control of variability, namely to deal with the deterministic matrix. So instead of the adjacency matrix, which is what was generated from the Pij's, let me just take the matrix of generating probabilities, P. And instead of the degrees, let me take the expected degrees. So all deterministic. And let me remove the corresponding space. This would have been this is a wonderful quantity. It's all deterministic. So the question is, how closely does it, how does it relate with the second, with the first eigenvalue of this quantity, which is what we really want to analyze. And so we have one way of rewriting the matrix that involves the random variables in a way that the variability is smaller. So we can write it as the sum of two matrices. One is this completely deterministic matrix, right? And another matrix which is completely stochastic matrix, and it is whether the edge appeared or not. So Aij of the adjacency matrix minus Pij, the generating probability, and we normalize by the square root of the expected degrees. And then we multiply, left and right with whatever we have to multiply to make the whole thing work. So the point is that this is a, new, as far as I know, way of expressing the matrix, and it is kind of crucial. So this normalization is kind of crucial, and this is the bottleneck in making the results go through for general, for large weights. And okay, so this is step 2. And once we have this, well, step 3 is, so there's a very nice bound by Wu, and it says that if we have a matrix where the expectation of each entry is 0, which is like the C, the variability matrix that we have. And if we can get an upper bound on the absolute value of each entry, and if the variance is large enough compared to how the entries vary, then you can get a bound on the first eigenvalue of this matrix. It's a, yeah. So, so technically, the limitations of the methods come, I think, from this way of bounding the second eigenvalue or the first eigenvalue of the stochastic matrix, and it is because so Wu's theorem is really tailored for regular graphs. So, I mean, by the way, you know, it can be extended when you don't have regularity, but you know, it assumes a uniform upper bound on all the entries of the matrix, and you know, a sigma that is large enough, and the point is that, you know, you could have edges in, you know, with probability 1 in the very dense part of the graph, which would make this sigma 0. So, you know, it's a limitation of the bounding method, and you know, this is a very sort of detailed and technical theorem. It improves on the Furedian-Komlosh theorem of, I don't know, 83 or 84, or and its proof is based on very detailed enumerative combinatorics of you know, computing the trace of certain matrices, and it's not at all clear how these combinatorics would go if, you know, the variabilities were larger. So I'm just pointing to, you know, where technically the limitation is coming from. Okay, and so these were the two theorems. Now, why are we looking for these theorems? This is the context. So let me say a little bit about the context of complex networks and, you know, what discrepancies are observed. Okay, so context of complex networks in one picture that we've been seeing for the last 10 years. There's vastly inhomogeneous degrees, and there's vast literature right now so far. And, you know, within a few months after, you know, people started modeling random graphs with inhomogeneous degrees, you know, there were, you know, objections. So people from networking came and they said, oh no, you know, in real networks. So if you see the intranet of Microsoft, they say no, the large degrees are not in the center of the graph connected to each other. The large degrees are, you know, the ones that take the signal, you know, and split it in the end to many, many different customer, you know, clients. And the small degrees are the high bandwidth nodes, and they're in the center of the network. Okay, so and then there's a whole bunch of mathematicians trying to mathematize this notion as negative associativity. Something was missing, is that there was semantics. So if in this graph, there's clear semantics. You know, there's high bandwidth node, mid bandwidth, low bandwidth, right? So, I mean, networks do not form to, you know, satisfy positive or negative associativity. I mean, they form for other reasons. Okay, and you know, how to capture these semantics. So, I mean, I'm just giving a reference. Actually, you know, with today's methodology, we can capture it very nice mathematically. But just to point out that, you know, immediately after the observation that degrees can vary vastly came the first objections that, but look, please don't keep giving me, you know, random graphs. Now here is discrepancy with respect to, so the first discrepancy was with respect to hierarchy. So you have hierarchy in the bandwidth of the node. So the second discrepancy is with respect to, so, you know, you can call it so with respect to existence of sparse cuts. So you can also talk about sort of clustering coefficient triangles, but I think, you know, conductance is much more interesting because it's a, you know, it's a global property, and so this is, again, you know, pictures. Okay, this is a picture for Flickr. What do you get if you input on Flickr the word graph? Okay, so some people mean something as a graph, some people mean something else, some people mean. very strong clustering. And it, it can go, very sparse cuts. And they can become arbitrarily sparse. This is some kind of social network of, collaborations and patents in the Boston area. Okay. So point is that there is semantics. There's underlying communities, and this will not be captured by, a random graph if you only model the degrees. And finally, this is so in 2008. Actually, this was a. It has become a very well cited paper at Yahoo. Leskovet, Mahoney, Faluzos, and Faluzos measured a whole bunch of real networks, and this is what they did. They were trying to see what was the sparsity of the cut. So conductance is on one axis, right? And then they were trying to see how many nodes the corresponding set involved. And there was major effort in developing algorithms. How do you find, the worst cut, for these many nodes? And but in a nutshell, a random graph that has a certain degree sequence, we all know it. It looks like this, right? So you have, as the sets become large enough, you get your constant conductance, and pretty much know what that constant is, 3/4, whatever, lambda 2. And then you get your sparsest cut around log n, right? So it is the small sets that present the difficulty. And what they measured is not only deeper cuts, sort of sparser cuts, but also repeated sparse cuts at larger and larger, involving larger and larger number of vertices of the graph. So and again, these are unquantified. So I don't know if this is log squared n or n to the 1/100. Who knows? But it is mind-boggling. If you know that all random graph models behave like this, and in practice, repeated with different methods and for different networks, you see something, so vastly different. It's something worth exploring. So, all right. So again, within the context of complex networks and the inhomogeneous degrees for which there is vast literature, here are two properties: hierarchy and clustering. Communities that have very clear semantics, and ordinary standard random graph models do not capture them. And so this is speaking towards extending the parameters of our random graph models, to start capturing in a mathematical way such properties. And I put here the work of Kleinberg, the seminal work of Kleinberg on the small world phenomenon, because so what was Kleinberg really saying? It's so yes, that you can navigate a graph, and that it and that you can do it in an algorithmically efficient way. But then, if you look at his mathematics, what was his mathematics really saying? His mathematics was really saying, look, there is further parameterization to be done, and please pay very close attention to the parameters, because it makes a big difference. So in retrospect. So we want to do something like this as people are, addressing discrepancy from networks, of random graphs from real networks. So here is what I think are, desiderata of a random graph model. Of course, it should be, predictive, sort of, as much as possible. Sort of, it should match the structure. If you're talking about, it should match the function. It should be explanatory. It should perhaps fit the semantics. So, okay, predictive, it's obvious. It should also be mathematical. It should be, amenable to analysis. So I think that, by now we've seen way too many anecdotal models. So, the real challenge is, it has to be mathematized, because only then can you be really predictive, and only then can you, point to, what are the parameters and how, if you tweak them, you're going to get, different function and And of course, they should be, efficient to implement. So if you're going to generate a graph on n nodes, it shouldn't take n squared time, or if we're talking about millions. So and the graphs that I'm going to talk about are efficient to implement. So here are 3 random graph models that generalize GNP. The inner product, random inner product graphs, which was all in Jung's thesis in 2008, and he had, publications before, and this is what I will focus. They are a special case of general inhomogeneous random graphs, which were introduced by Bolobas, Jansson, and Riordan in 2007. This was sort of independent work. Essentially, the Bolobas, Jansson, and Riordan model is whatever I'm going to talk to you about, except you can replace inner product with a much more general kernel function. Okay, so it's a special case. And then there's another, all generalizations of Erdős-Renyi, right? So, and then there's another class that I'm not going to talk about, stochastic Kronecker graphs, which is also a generalization of Erdős-Renyi. So we are exploring all options to see what one can get. So this is the model. All right. So the vertices are in d-dimensional space, and d is fixed, independent of n, right? So it means that no matter how large the graph grows, every node can remember d things. I can remember 100 things. It doesn't matter how big the population becomes. So there's like d relevant parameters, and every vector is a point in d-dimensional space. Okay, so 1 dimension for each relevant parameter. So the vertices are going to be vectors in d-dimensional space, and how are they going to be generated? Well, there's a probability distribution mu in d-dimensional space, and mu is also fixed, independent of n. All right, and this is essentially the only new parameter that only one parameter that we are introducing, that points are generated according to a distribution in d-dimensional space. And how do vertices connect? Well, there's a probability between there's an edge between 2 points with probability proportional to their inner product. Okay, so I'm making some assumptions here that, the vectors have positive entries, and okay, so it didn't have to. I could say the minimum of 1 and the inner product of 2 vectors. So this is the nature of the model, okay? And again, the more general model would be if instead of the inner product, you could have, some other, kernel function. All right, and we have to introduce a couple more things. So one is that you realize that because mu is fixed in d-dimensional space independent of n, this could generate, very dense graphs which are not particularly interesting. So for example, if mu was focusing on 1 point, 1/2, all of mu was on 1/2, you would be generating, Erdős-Renyi graphs with, with average degree n over 2. That's not interesting. So we are going to divide by, all right. So then we have a sparsification function. So that's the other parameter of the model. So we are going to divide by a sparsification function. We can choose whatever we want, whatever we think it's appropriate, but something to make, the graphs interesting, to make them sparse. And the ones that I am using is at least log squared n over n. So it is so that the line theorem and the thin cone theorem that I told you before pass, and it is also, I need at least log n over n to talk about, to get connectivity in the first place. All right, so this is the model. Mu fixed distribution in d-dimensional space, a sparsification function g of n, which is not too small, and endpoints in d-dimensional space generated according to mu and connected according to their inner product. And I'll put one more condition, and this is that these points have some weight, so that I don't get disconnected for trivial reasons. I mean, if the distribution goes to, if mu, the generating distribution, goes to 0 too fast, you won't get connectivity because points are just not interested in the network that they are participating. So it's a technical condition, it's just to ensure connectivity. And that's it. That's the model. And what would be the strategy outline to get conductance? Well, I can show conductance for cones, right? For thin cones, as I said before. So I want to, I'm going to decompose the graph into thin cones, right? So I will say how this decomposition is possible and why it is possible. And in fact, the thin cones that I'm going to decompose it will depend on mu. What is the generating distribution? And I will, I already know what is the conductance inside a cone, and then I need to argue about, connection across the cones, and then apply sort of relatively standard Markov chain decomposition or graph decomposition theorems. So, all right. So, so the point is that because so the point is that the decomposition can be done so that we have a fixed number of cones. So there is for the random graph model, there is a representative graph R, which is the red graph that you see here, which has a fixed number of vertices. So there's a very small description of how the entire model behaves, and it is a weighted graph. I will say what the weights are, and it is the conductance of this very small graph that characterizes the conductance of the entire of the random graph that is generated, and now you can see why I say that it's a little bit closer to real networks, because I mean you can imagine that we could just simply have 2 points very far away, and then already you would be getting your sparsest cuts at very large values, and they could involve cut sparsity much larger than much deeper, worse cuts than you would get in Erdős-Rényi graphs. Still, I'm working within constants, but they're different constants. That's the point. Now, how do we do the decomposition? So mu is the fixed distribution in d-dimensional space, and so what I'm going to do is that I'm going to get regions, cones actually, in d-dimensional space, such that the measure of the distribution on each one of these cones is a constant, and there's a fixed number of them. Fixed independent of it. There could be many, but they're going to be fixed. And okay, so here's a fact that unless mu is trivial, meaning a point or a line, in which case it's Erdős-Rényi or a thin cone, you can do arbitrarily fine but fixed decompositions of mu. Here's the reason why. Well, suppose that mu is bounded. So suppose that it is on a sphere, that it is a sphere. Well, then everybody knows that we can cover a sphere with smaller spheres of small radius, moreover a fixed number of them. And we can do the same with cones in d-dimensional space. And then we can use this covering to get the decomposition that we want, right? So we start with the first relevant sphere or cone, and then and that has constant that attracts a constant fraction of mu, and then we can get to the next one, just subtract what you've already counted, and then we get to the next one and subtract what you've already counted. It's sort of straightforward. Okay.
What is mu I?
Where is mu I?
Right there. Mu I.
Oh, that must be a typo. I don't know why I would have written mu I. It should have been mu on omega I. Let's see. Is it a typo? Do I have mu I elsewhere? No, it's mu on omega I. No, it's a typo. Mu I is a typo. Okay. So, yeah, mu. Oh, no, now I'm going up. That's not, oh, no. Okay, now I messed up. Okay, there you go. And how does this decomposition of mu, so now I talked about decomposition of the generating distribution. How does this suggest a decomposition of the graph? Well, in expectation, each class has a constant number of vertices, and so it is constant n. So I get the conductance that I need, or the bound on lambda 2 that I need for each one of the classes inside the class. And then, okay, so these are sort of the restriction graphs to follow Markov chain Monte Carlo terminology. So these are the restriction graphs inside each cone. And then I get the projection graph, which is what happens across the cones. And the representative graph that I was talking about is going to have one vertex for each partition class, which was dictated by mu. It's going to have a self-loop, which is going to be the volume of the number of vertices of this cone within itself. And it's going to have weights on the edges going across partition classes, which is the expected number of edges that go across partition classes. And here's a theorem. If mu is bounded, meaning inside some large sphere, or mu does not go to infinity too fast, the reason I need this is so that I can apply the cone theorem, and the cone theorem was saying that the largest xi has to be 1. This is artificial. This shouldn't be there. Okay, so this condition shouldn't be there. Mu is strongly non-orthogonal, means that the measure of pairs of points that have inner product close to 0 is 0. So you are away from the axis, right? Then the representative graph, which we already said is a graph on a fixed number of vertices, is connected, and the weights on its edges is independent of n. And the conductance of this graph, which is independent of n, but of course could be very different than the conductance of random graphs, lower bounds the conductance of the random graph in the random inner product graph model. And as I said, the specific techniques is just to decompose into thin cones and consider the restriction graphs in the thin cones, and then Markov chain decomposition theorems to argue across the cones. All right, so I think it's important to characterize more general mu, the more general mu being the one on the line. Forget the dimensions where you get points, that have higher weights. We need finer distinction of behavior of conductance. If you remember, in one of the pictures, the cats were not just sparse, they were very sparse. So it seems to be that the general status of affairs in this sort of area of characterizing conductance is that we have sharp, so either the conductance is 0 or the conductance is a constant. Well, no, I mean, in real networks, there seems to be a much wider range of behaviors. And by the way, this is also the case in stochastic Kronecker graphs of Leskovec, Paloutzos, and Kleinberg. Okay, so And I believe that if we start including orthogonalities, sort of the notion of how mu approaches the axis or touches the axis, then that might be a starting point of getting much finer behavior on conductance. Perhaps mu could be a variable, could be a function of n, though that would challenge very much the decomposition methods. But okay, so I think this is an important direction to follow, to characterize mu that includes almost full orthogonality and let mu be unbounded. And then in a different direction, okay, so as our random graph models become richer and richer, we see graphs generated from matrices of probabilities, P, right? So how can we relate the properties of P with the properties of the generated graph? And I'm raising this because, okay, so I mean, in this case, it so happened that the relative, that the generating matrix, was some P, and then there was a quantity involving so many random variables, and then we were able to control this variance, essentially saying that it is really P that determines, in this case, sort of the behavior, and can this be generalized? But just an indication, towards looking for stronger methods. I guess sparse graphs. Well, yeah. I mean, so these graphs have average degree log n. So we want to go to lower, sparser graphs, in which case either we have to look at the giant components, the behavior of the giant components, or we have to go to different models, like the configurational model, for which we get connectivity at much lower degrees. I think the reason I really put this last bullet on is because it is really folklore, sort of even in sparse graphs, even in the range, at sort of constant degree, Erdos-Renyi. So look at the giant component, once it has formed. And, okay, so there are sparse GATs, but what is their sparsity? How many? Of what kind? How many nodes do they include? Okay, these were things that were not important when we were only looking at, showing that graphs have good conductance and all eigenvalues were bounded away from 1. But if you start looking at existence of sparse GATs, there has to be a systematic characterization of, how many GATs of what sparsity, for random graphs, so that we start comparing them with models. And I guess that's all I had to say.
Questions? For the last bit, so that you're also asking about just a question about GNP, for P, when NP is a constant.
Well, I guess if P, yeah, well, okay. So let me tell you now the full story. So this is a nice picture to use in talks for explanatory reasons. But when I asked these people, I actually, John Kleinberg and I interrogated them to see exactly what graphs were going on here. These were very sparse graphs. So they had average degree. They told us in sometime it was 5, 10, these are very, very sparse graphs. So, you know, and you know, they were measuring, you know, large cuts of deep conductance. So, but these were sparse graphs. So, you know, what can we say? I mean, perhaps what they measured was consistent with what exists at, you know, but the point is that I mean, we know that that even when we have constant expansion, conductance in any random graph model, I mean, we know it. We see it in the calculations. We can prove it, you know, that, you know, with high probability, there will be a set that has, you know, pretty bad conductance, and it's going to be a small one. This is where the variances are large, around size log n. And, of course, if you go to large sets, you don't have a problem. So I'm asking, you know, how many of them are there? Of what size? So as to, you know, now these people were working in the sparse range, but if people start drawing pictures like this and say there's discrepancy, we might as well understand, you know, in full detail, you know, where are the sparse cuts, what kind of sparse cuts we have, and I mean, that's a project in its own right. Yes?
So your methods here are based on looking at the second eigenvalue of the matrix.
Yes.
But has anyone tried to study conductance by looking directly at all subsets and estimating the number of edges they use?
Yeah, so this is sort of always the first approach, you know, probabilistic counting and take union bound. It does not work in this case. I mean, it works very well if you're dealing with a configurational model. It does not work well in this case, and in fact, you need very detailed trace methods, you know, where you need to count the probability that you return back, you know, these are the only methods that we know for.
But you said it works for configuration model.
Yes. But the configurational model has much less variance than this model. That's the problem. Yeah? So, I mean, you have lots of dependencies, and the dependencies the configurational model help you. And here you have independence, which you can use. But in this case, it does not help. No, I do not think that, you know, as you generalize the model so much, I mean, I think the trace method has limitations. Either that, or we have to get inside its enumerative combinatorics, which are quite non-trivial, you know, and fix them. So, I don't know. I mean, it's something frustrating, or maybe conductance is not the correct measure. But it's very frustrating that, you know, we clearly see better behavior in graphs, but just this inhomogeneity creates this problem. I mean, what you suggested before, monotonicity, no, it doesn't go through per se for conductance, but, you know, some monotonicity, not any monotonicity, because you can start plugging, you know, clicks in wrong places. But so there's limitation in technique, and I think actually the inner product model is good because it sort of has the right amount of difficulty, like not too much, but enough that you can start working and, you know, say something. Yeah, I mean, it's a good test point.
One option to emphasize besides the conductance is to look more at the spectrum, at this isoperimetric or conductance profile. So for sets of different sizes, what are the best cuts?
Yes. Okay. So this is another thing, and this is a discussion. You know, it comes up. Actually, yes, not actually when you're talking to sort of social networking, you know, people that work on social network, so they think we have a fixation with the second eigenvalue, and we try to measure it, and so they keep coming back, and so what did we learn? Okay, so per se, you don't learn very much, right? But the point is, what you're really interested in is the eigenvectors and how they behave. You're interested in the entire spectrum and how does it behave. these are much harder problems. So the second eigenvalue starts being an indication that you can put.
Looking on the conductance side to look at, maybe you have small conductance because you have some small, some small sets that have even smaller boundary, but you could say I'm only worried about sets from a certain size on. And
then it's wonderful. Yeah, I mean, yeah, if you're interested about large sets only, there's no problem. But no, so I mean,
it's kind of maybe what threshold you start being interested in matter.
Okay, so yeah, sure. So
this Lovas-Kanan mixing time estimates.
Yeah. So I mean, I would not disclude the log n area from an interesting area. Let me put it that way, or polylog n. And in that area, I mean, I would not say some constant and above. I mean, or some n to the 1 over 100 or n to the epsilon and above. I mean, I think the polylog n area is important, and that is precisely where the methods break down because of the variance.
Any other questions? Yeah, then let's thank the speaker.
Thanks to the hosts.